It's spellers.
I am.
Yeah. I'm not judging one way or another. It's spelling is not something you necessarily need to pay attention to anymore. I mean, if you use Word,
Good enough.
Word checks for you. It even checks your grammar for you. AI is the next generation. Use it. It's a tool. However, don't let it think for you. You can take my labs and paste it in ChatGPT and it'll write a lab report for you. It will be a terrible lab report. Maybe in 2 or 3, you try. Maybe in 2 or 3 years, it'll be a fine lab report. I mean, you may get away with it. I don't know how good the TAs are. So, I mean, there's the thing.
Other than Alex, yeah.
But I mean, in some sense, I'm not invested. So if you're cheating in the class, yeah, maybe you can get away with it. I care, but I don't have the time to micromanage. So, that said, I will give you the advice. If you can't do the job when you get a job, you're going to be working at McDonald's. So,
Flipping burgers, call my name.
yeah, $15 an hour, well below poverty wages. What's that?
There's a button position that they need an engineer for.
No, I mean, a few, but there are people that shuffle paperwork around. Anybody watch The Office?
Yeah, that's good.
So not the television series, the movie. Yeah. So, there's kind of a funny thing about engineers in the movie. It's a good movie. I would recommend it. Anyway, so back to our topic at hand. Where are we? There was a prep assignment that was due before class again. As usual, I hope everybody did it. I just bring this up because I want to remind you. Where's down? There we go. We of course have the excitement of a homework due today, but I'm sure you're all done and posted already, so I don't really need to say that. And then we'll have homework, of course, due on Friday. We did wrap up our lab yesterday, or at least I hope we did. If not, then we'll arrange some time for you to get into the lab space, if you need it. And then we will start lab 2 next, whatever, Monday, I guess it is. Yeah.
Is that normal for it to be a two-parter, or is that an anomaly?
I think most of the labs are 2-part. There's 1, 3, and 1, 1. So, I mean, one of the things, you don't care about the history. It's better this way. Less lab reports for you to write. Yeah, my history, it's fine. My teaching history. You don't care that much. What else do we got going on? Test isn't for a couple weeks. I think it's not for 3 weeks, if I remember right. March 12th. March 12th? So, is that like the week before spring break or something like that?
So we don't have as many tests in this?
Only 2 tests in this class.
Oh, man, then the stakes are.
2 tests in a final. Two exams in a final. Quizzes, yes, quizzes.
Why not tests?
Because they're just quizzes. They're not very hard.
You gotta look at it multiple times.
I mean, everybody says my tests are pretty easy, so.
Didn't they say that all the time?
They said that about circuits. They say it about it. Electromagnetics. All my classes are easy.
2020.
Is that an RPI test?
Are the RPI tests actually harder?
Longer. I had 2 hours. So they're longer. All right. So I think that's all our administrative stuff. We have anything else that I needed to talk about? Everybody's applying for jobs. I probably haven't asked that nearly often enough this semester. What's that?
Job market a little rough right now.
Job market's weird. There's a lot of turmoil with regard to what's going on with the federal government. So companies are kind of trying to figure out what to do. Yeah.
But they still do this year.
Yes. So they are doing SERP. SERP is Albany sponsored undergraduate research program over the summer. And I did want to submit for SERP, and I wonder if I missed the window. Forgot. I forget. I'll have to check. What else? I don't know. All right.
Oh, I got it.
Okay. I'm listening.
For our first test, Is it gonna, so I know it's two now, or next flat. So the first test is gonna be,
Amplifiers and diodes.
okay, that's it, and then the next test will be the next two, and on the final will include everything.
Yes, mine will be comprehensive.
Mark 4.
I don't remember the calendar off the top of my head.
Mark 4.
All right. So one of the things that about a third of you missed last Thursday is our discussion of finite gain. So op amp finite gain. And that is in the homework, and I tend to call this a op amp. And we know ideally this goes to infinity. Practically, this goes to somewhere around 10 to the 5th volts per volt. So it's a big number. Ideally, it's infinite, but in practice, it's 10 to the 5th or so. That said, one of the things we looked at last class, at the end of last class, is here's our op amp, and I queried you about something interesting about this circuit. And almost everybody, having read through your sheets, said the capacitor in the center there is kind of an odd thing. Why is that capacitor there? And so that capacitor is there to give us a low frequency cutoff. Low frequency characteristics, and I'm going to add a little comment here, that are known. Or I should say low pass characteristics, not low frequency. Let's call it low pass. Sorry about that. Low pass filter characteristics. So we saw that in the lab yesterday. I hope, hopefully with some success. I can add a little side comment that unfortunately our class is a little bit out of sync with our lab, and for that I apologize, but there's not really a lot I can do. So I think at some point we catch up, so to speak. So anyway, that capacitor's in there to give us low pass filter characteristics that are known. I can add the side comment in that something we may have talked about in circuits. And when I build a circuit, there's always something called parasitic capacitance. There is capacitance everywhere. This room has capacitance. So there's rebar in the ceiling, rebar on the floor. That's a parallel plate capacitor. I mean, it's a tiny capacitor. It's probably 10 to the minus 20 or even smaller. So it's a negligible capacitor, not important, but it's there. It exists. Left wall, right wall, there's a capacitor there. Front, back, whatever. In our circuit, we can go and look at the traces that interconnect. And there's a more reasonable capacitance there. So when you lay wires on your circuit, depending on how close those wires are, we can get capacitance. And I've done that as an experiment before. And if you want to see that, I'm happy to demonstrate that. You can do things like capacitively connect two things, or without having an electrical contact, so you can use them as antennas, so to speak. But also, every transistor, and we'll touch on this a little bit later in the class, every transistor has a parasitic capacitance associated. Parasitic, if you're not recognizing the term, means it's a capacitance that we didn't design. This capacitor is part of the chip. We built this, we designed this. These guys, every transistor or the traces, they have capacitance that are artifact of the physics of the universe. So we can't get away from them. They are there. When we build a model for the transistor, we will see capacitors. So that said, in order to give us a chip that's reliable, this capacitor is added. And what does that mean for us? Well, going back to this stuff, namely this one, when we talk about the op amp having finite gain, not only does it have finite gain, but it is frequency limited. It has low pass filter characteristics. So the gain of the op amp has low pass filter characteristics. And that's kind of a counterintuitive comment. So the gain itself changes as frequency changes. This one? Water bottle upstairs. Good. So a op amp is a function of omega. Why am I writing that out? Previously, namely last class, we considered a op amp to be constant. That is not the case. So to go and look at a circuit for a moment. Everybody good? I was gonna flip to the next page. Are we good? So I'm just gonna do this circuit. This circuit has a name. Anybody remember what it is? Anybody remember the circuit? We brought it up before. No one? That's the chip. What's the circuit? It's a comparator. So the output goes high or low. A little bit more realistically, we can say V out equals A op amp times V in. Or if we want, we can write V out over V in, which is our familiar what? What is that? Our transfer function, H of S equals A op amp of S. I'm going to drop the amp just to make it a little bit shorter because I don't write fast enough. You guys think I moving too slow. So the op amp gain is a function of S. What I want to do for a second, I want to go back and grab, this is here. I want to grab Bodhi paper. Where do I have Bodhi paper? Circuits. When did we do Bodhi plots? Ah, there we go. Back in the day.
The good old days.
The good old days. Weren't Bodhi plots, don't they seem simple now? Everything in circuits seems simple now, right? Everything's hard now.
Just real quick, what does it mean to have capacitance?
What do you mean?
Like, you describe that this room has capacity as well. What does that?
Oh, from a circuit point of view, we can model the power connections coming in as a circuit and we can add capacitance. In this case, it's totally negligible. But so anytime you're modeling anything in real life, and that's what we're doing, we're trying to represent a real world circuit as a model. And what we will see in this class especially is our models can be improved upon. So as part of the lies I tell you is, I mean, that's what we've been doing all along, I suppose, is we've been modeling our op amps, adding more and more features to show their limitations. So our ideal model for an op amp is the gain is infinite, the input impedance is infinite, and the output impedance is 0. And if we do that, Vn minus equals Vn plus, In minus equals In plus equals 0. But then we introduce DC biases where In minus and In plus are not equal. We have a DC voltage offset. We introduce finite gain where Vn minus is not equal to Vn plus. So those are the things we're doing. So anyway, we can plot a op of S or J omega. Remember, S and J omega go hand in hand. So that said, our op amp gain looks something like, I'm going to put this on the bottom, get a little bit more room. A op amp over S plus, getting a little careless here. Times omega B over S plus omega B. A op is a constant term. That's the gain of the op amp that we've been using. And again, for us, it's around 10 to the 5th. If we go back to the spec sheet, it was 2 times 10 to the 5th, but 10 to the 5th is a little bit easier. And omega B is the break or cutoff frequency. So for the op amp we just did on the previous page, this op amp, then we can plot something that looks maybe like this. Remember, this is log of omega. And we can have -1, so that just means log of omega is 0.1. So I suppose just to remind ourselves, this is 0.1, that would be 1, that would be 10, that would be 100, that would be 1,000, that would be 10 to the 4, 10,000, that'd be 10 to the 5 radians per second. So there's our Bode plot. And then on this axis, we have dB. And our plot looks something like this. Lined up here. There we go. So we have 20 log of 10 to the 5th, which if we do that math out, hopefully you all remember, is 100 dB. So there's 100, there's 80, there's 60, there's 40, there's 20. I should have moved it up scale. I didn't have to redraw this, unfortunately. And then down here we have 0. So if I extend my plot and I need that 0, then we're going to have 0 down below. And I will redraw this. Unfortunately, I didn't pick the right scaling factor, but be that as it may. There's our standard Bode plot response. But what we're saying here is the output for this circuit depends on frequency. That's exactly what low pass filter is. So if I'm at very low frequency, namely around 1 radian per second or 5 radians per second or something like that, the output is 100,000 times the input voltage here. This is the comparator circuit. I've actually tried to build this circuit, but you need a voltage source that has a, you can set down in the microvolts range, maybe 20 microvolts or something like that, in order to actually pull this off. Scopy, this is impossible. The smallest voltage setting we can do on Scopy is around 2 millivolts or something like that. And even there, it's noisy as hell. So this is not a realistic characteristic, but if I went up in frequency, so if I went and said, all right, I'm going to apply a signal that's, 10 to the fifth radians per second, and it's a 1 volt signal at 10 to the fifth, then at 10 to the fifth, my gain is 20 dB, which is 10. So if you go back and forth between dB and gain, something we did in circuits, something you should remember how to do. We have a gain of 10, and then we have an output of 10. So our output of our comparator would be 10, and we would be flipping back and forth. 10 minus 10, we lose it. And that maybe we could do, and maybe I should set that up as an experiment. We can see the effects there. It's not the motivation here. The motivation has to do with what happens when we have something along the lines of our inverting op amp. So here we have our inverting R2 over R2 and R1. There's our V in, there's our V out. And due to finite gain, we had V out equals, minus R2 over R1 plus R1 plus R2 over A op amp times Vn. That was the derivation we did last class. That's old news. So we did that discussion last class. We used circuit analysis. You had to do this something comparable in the homework that's due today for the non-inverting op amp. Do our circuit analysis and we get that result. Something to point out, and we brought this up last Thursday, is in the limit as A op amp goes to infinity, this term goes to 0, and we're left with minus R2 over R1, giving us that ideal relationship. Right? We talked about that on Thursday, so it's a little bit of a rehash. What I haven't done, or what we didn't do on Thursday, was add a little bit more complexity here and say this is a function of S. And we just drew that. So I could do all this in the S domain and say this is V out of S. That's Vn of S, because A op amp is a function of S. A op amp itself, the gain of the op amp, has these low pass filter characteristics. The gain of the op amp includes 2 parameters we just wrote. That, the gain, the low pass gain parameter, which is a constant, and the cutoff frequency. Every low pass filter has that, right? Everyone agree? So that said, I can go plug that in. We can look at our transfer function characteristics. I can bring Vn to the other side. And I'm going to rewrite this a little bit. R2 times A op of S over R1 plus R2 plus just reordering things times A op of S. This gives us a little bit cleaner algebra to work with maybe. And then I can substitute in our expression for A op of S. So there's R2. I'm reusing A op here. There's the constant. There's our low pass, or there's our passband gain, S plus omega B over R1 plus R2 plus, in this case, R1 times that constant. A op in this case is a constant, kind of switching my subscripts back and forth, S plus omega B. I'm just plugging in my low pass filter characteristics for the gain of the op amp itself. Everyone agree? Are we okay? I find this to be kind of a subtle thing, and the net result, I think, is fairly simple, with the process of getting there is a little algebraic, and thinking of the fact that the op amp gain itself is a function of frequency takes a little bit of practice, I guess. So, little reorganization there. We get R2 AOP times omega B over R1 AOP times omega B plus S plus omega B times R1 plus R2. So what do we see here? And again, there's a little bit of geometry. This is a constant term. Omega B is a constant term. I suppose we can take that a little bit further, do a little bit more algebra. R2 AOP times omega B S times R1 plus R2 plus omega B times R1 plus R2 plus R1 times AOP times omega B. A little bit of rearranging, and we get something that looks familiar. As we look at this, I suppose, we can kind of relatively compare these two. So omega B is a small number, 10 radians per second, we said. That's actually part of the design. So we don't have to do that, but that is typically, that cutoff frequency of the op amp itself is typically a small value. Yeah.
How do you introduce omega B into the equation?
I just gave it to you. So there's the low pass filter characteristic. So the op amp itself has a frequency response that looks like this.
Just plug in for that.
Yeah. So I just called it omega B to give us low pass filter characteristics. That capacitor gives us this omega B. So that capacitor in series with some sort of equivalent resistance, one of our RC type of effect, gives us that omega B. So again, I mean, there's no easy, at our point, no easy way of saying what's the 1 over RC effect here. I mean, we see our capacitor and there's some equivalent impedance looking in, that capacitor sees some equivalent impedance, but there's no easy way to derive that. It's a big number, giving us something that's relatively small cutoff frequency. So it's not, unfortunately, typically reported in spec sheets. I did look through a few just to see. As far as I can tell, it's usually not reported. I should look through some more and see if I can find it. But yeah, it's a good question. That said, there's our expression, and we had some discussion about this. So what are reasonable values for a op amp? 10 to the fifth. That's what we're using. For the 741, it's around 10 to the fifth. What are reasonable values for R1 and R2? In the kilo ohms, maybe up to 100 kilo ohms. We did use an R2 in the 100 kilo ohm range. We have a common omega B, common omega B. We have this number, which is on par with these two numbers, but then we multiply by R1. This is largely negligible. So we can approximately say, and this is an approximation, that this winds up being R2 times AOP times omega B. And I'm going to do, well, I'll come back to this in just a second. R1 plus R2 plus R1 times AOP times omega B. Now, I am going to do a definition, and those of you who did a little research or looked in the crib sheet, this is there. There is a concept called the gain bandwidth product. I'm doing this because I just want to introduce it as a term in our expression. GBP. The gain bandwidth product. And it turns out, to formalize our definition, the gain bandwidth product is what I call A circuit times omega circuit. Or we could alternatively do F circuit. And I think in the spec sheet it is F because this has units radians per second. This has units hertz. What's the difference between those? 2 pi. That's it. So it doesn't matter which one we choose. We can always go from one to the other. Remember, omega is 2 pi f. So I tend to stick with the top one just because my Bode plots are in omega, but you can find Bode plots in F as well, in hertz. This is a boxable equation. A circuit is the gain of the circuit. And I should point out in magnitude. So minus signs go away. Someone asked me that, just to add that clarification. When we talk about gain, we usually talk about magnitude. Minus signs are phase terms, they matter. But I don't spend as much time with phase in this class as you would, say, in advanced circuits. Omega circuit is the cutoff frequency of the circuit. It's the corner. It's the 3 dB point. Minus 3 dB. And just to emphasize, 3 dB implies a minus sign. So for our purposes, for the op amp, itself, this guy, this circuit, this, and this are our parameters. There's the gain of the circuit. There's the cutoff circuit. So for the op amp itself, A circuit equals A op, omega circuit equals omega B, from A op of S equals A op times omega B over S plus omega B. I know I've had that in the numerator. It doesn't matter. I factored it out. From the low pass filter characteristic of the op amp itself. So when we're running this as a comparator, then the gain of the circuit is the gain of the op amp. So all that said, we can go back to our discussion here and use that feature. So we've already made some approximations. So continuing back to our discussion for the inverting op amp, H of S equals V out of S over V in of S. Remember, we're looking at transfer functions here. Equals R2 times the gain bandwidth product, doing that substitution, over S, times R1 plus R2 plus R1 times the gain bandwidth product. And do one more step here, 2 more steps. We want to get rid of that coefficient associated with our S. So we can write this as R2 over R1 plus R2. And somewhere along the line, I dropped my minus sign that should have been carried along all the way. GDP. over S plus R1 over R1 plus R2 times the GBP. I'm going to make one more approximation, and these, we've already done some approximations. These should all be squiggly lines. Typically, R2 is much, much larger than R1. It's an inverting op amp. I mean, this is part of our approximation. And if that's the case, then we can take this and write, if R2 is much, much larger than R1, what's this term? What is this term? 1. Approximately 1 times the GBP. S, and then what's this term? There's that minus sign that I keep dropping. R1 over R2 times the GBP. So there was a lot of kind of hand-waving approximation here, but what we recognize is this is a cutoff frequency, omega C, and we can recognize that this is a cutoff frequency. So if we write GBP times R1 over R2 equals omega C, then we recognize that omega C is, kind of doing this a little bit weird way, R2 over R1. Just taking this and putting it in the denominator. And what's R2 over R1? That's the gain of the circuit in magnitude. Magnitude of the inverting amplifier gain. In other words, it's a circuit. Are you all right?
Oh, sorry, I took some caffeine.
Okay, it looked like you were questioning something. No, just checking in.
Nah.
Okay. So a circuit, we already knew this, is approximately R2 over R1, magnitude of a circuit. Let's point that out. We do have a phase term. And the cutoff frequency is the gain bandwidth product over the magnitude of a circuit. And that's the moral of the story. So there's omega C, or to go back to how we defined it, there's omega circuit. The GBP is a known property. For the op amp. It's a fixed. I say no, and I mean spec sheet. And we can go look that up. So if you're still writing, I'll come back to this. Don't worry. But it's not, in some cases, it's called the gain bandwidth product. I've seen it written as gain bandwidth product on some spec sheets. In this one, it's not. It's just called bandwidth. But there it is. So somewhere around 1 megahertz, 1.5 megahertz. I realize the other two aren't listed. Every op amp has a gain bandwidth product, but it's a spec sheet value. It's a fixed value. I give you an op amp, you buy an op amp, whatever, it has a gain bandwidth product. So
Other term for the game damage product, like closed loop bandwidth. That's what.
So it would be, the gain bandwidth product would be the open loop bandwidth. The closed loop bandwidth is what we're getting at now. So, and that's a little bit of terminology I should probably comment on for just a second. Go back and look at our circuits. This is an open loop circuit. Why is it open loop? Because there's no feedback. The output is not connected to the inputs. There's no feed. This is an open loop circuit. So if you take advanced circuits, this is a discussion that comes up. They use a little bit more circuit related terminology, something I've been trying to incorporate and I tend to forget. This is a closed loop circuit because we have a feedback going from the output to the N minus. So here's the closed loop equivalent amplifier circuit. Does that answer your question? So that said, the closed loop bandwidth depends on the gain of the circuit. The cutoff frequency, the corner frequency for our inverting amplifier depends on the spec sheet value, but specifically, the thing that we control depends on the gain we've designed. So omega inverting, which is omega circuit, just is the GBP, and put a little approximately in there, over a magnitude of R2 over R1. There's the gain of our circuit. And that's just this formula that we boxed up, plugged in values. So what we should have seen in the lab yesterday is as you increase the gain, the cutoff frequency went down. The passband gain went up. So we have more gain, but it was a valid answer, a valid gain over a smaller frequency range. Is that consistent? Everybody feel like they saw that in the lab? It's an important thing to say yes. See, 2 yeses. No?
Question.
Did you do it? And you didn't see the gain change. All right, so then you have bad data. Okay.
So specifically with the gain of the circuit, the gain of the circuit in this case is the gain of the op amp, like always.
No.
Okay,
So
I just want.
the gain of the circuit is, in this case, the gain of the circuit is the gain of the op amp,
In this case.
which is a fixed value, a spec sheet value. In this case, the gain of the circuit is minus R2 over R1, but we're doing magnitude, so it's R2 over R1. And that is a design choice. We can go pick different resistors, different gain.
Right.
Same with the non-inverting op amp. Same with the difference amplifier. Any of those circuits, we pick the components, we pick the gain. So you should see low pass filter characteristics. I'm going to give you a thought problem. Now, before I do that, I still have this. No. So we're going to go back and do something along the lines of what we did. 0, 1, 2, 3, 4, 5, -1. I'm going to actually start up here at 100 dB. And I do that because then we have 80, 60, 40, 20, 0. Where the stop band crosses 0 dB is the gain bandwidth product. Remember, GBP has units, either radians per second or hertz, whatever your preference is. That said, this would be a comparator circuit. Well, I could do an inverting op amp with a gain of 1,000. And a gain of 1,000 is 60 dB. I would have something that looked like this. We have that same. God dang it, I drew that wrong. That's annoying. Come on. I drew my slope wrong. I'm sad. Big enough. Ugh. I need more plot. Well, I'm trying to figure out how to do this a little bit differently. Let's just change the scale. Not my first choice. All right. Yeah, I'll fix it just a second. Here is 0 dB. Oh, that shouldn't say 100. I didn't pay attention to the fact that I missed the vertexes. Here is our GBP now. The reasoning applies. The same story applies. There's 0 dB. Why is this not coming out right? Oh, my scale's all off. God damn it. All right. Sorry, that was awkward. But and in this case, because the values I picked, we get a GBP of 10 to the 7th radians per second, which is perfectly reasonable value. So my corrections aside, everybody kind of see what I did? I picked a omega B, that was a choice. So I just changed it. It's a low value, it's a reasonable value.
You're trying to cross 0 dB at
10 to the 7th. So this is at 10 to the 7th. I realized that was confusing and I shouldn't have done that, but I should have been paying attention. I was a little careless in trying to fix it too quickly. Are we good?
Are you still gonna draw the gain of 1,000?
Yes, I will do that imminently.
So 10 to the 5th level.
The 10 to the 5th is a gain of 100 dB. There's our passband gain. So that was a op amp is 10 to the 5th. A op is around, oops. Stop that. 10 to the 5th volts per volt for the comparator. All right, sorry about that. Are we okay? That said, now to go back and do what I was doing here is my inverting op amp. Inverting op amp with a circuit equal minus 1,000, 10 to the 3. And our cutoff frequency is 10 to the 4. And that checks because for this, omega C is GBP over a circuit in magnitude is 10 to the 7th over 10 to the 3 equals 10 to the 4. I lower the gain. I have less gain, but I have a larger bandwidth. And we can put in another example and it's the same story. So again, the moral of the story is high gain, low bandwidth, low cutoff frequency. Low gain, high cutoff frequency. That said, once we hit the stop band, it doesn't matter what circuit we're talking about. Everything has the same slope in the stop band, and we intersect to have the same stop band. So I could do a circuit with a gain of 100, and that would hit the stop band and then overlap once again. So this would be inverting op amp, a circuit equals minus 100. Any value. And the cutoff frequency is now 10 to the 7th over 100. Sorry, that's gain of 10. Not 100. Too many mistakes today. Gain of 10, 20 dB, 10 to the 7th over 10, cutoff frequency of 10 to the 6th. So, moral of the story again, cutoff frequency depends on circuit gain because of the op amp characteristics itself. A little bit more time than I wanted to spend on this. But it's a real concern. That said, here's an example challenge. GBP equals 10 to the 6 radians per second. Design goal. A overall equals 10 to the 4 over a frequency range of 10 to the 5th radians per second. You can call that omega C if you like. If I just designed an inverting op amp with a gain of 10 to the 4 and my gain bandwidth product is 10 to the 6, what's my cutoff frequency? Are you leaving?
Sound.
What's my cutoff frequency? Not quite. 10 to the 1. If I have a single inverting op amp with a gain of 10 to the 4, meeting my design goal here. 10 to the 2. Do I meet this spec here? How do I do this? It's possible. How would I do it?
Oh, I see.
How do I do it? The homework problem you're gonna have. Who says I only need one stage? I can design a circuit with a gain of 10. What's my cutoff frequency then? Still a little awkward, but then it would be 10 to the 5. I could have 4 of those. It doesn't quite give us what we want. But you could have multiple stages in a row, low pass filter, low pass filter, low pass filter. And we want our cutoff frequency for each of those low pass filters to be larger than our overall cutoff frequency. So in this case, I kind of
Is there a way to do it without having a lot of speakers?
get a better op amp maybe. So, you know, get one with a gain of internal gain of 10 to the 10. I don't know if they exist. The largest I've seen, I think, is around 10 to the 7th, but you know, spend more money, maybe. Solution. Multi-stage circuit. We have some H of S equals a circuit over omega circuit over S plus omega circuit. 1, 1, 1. Repeating. That was interesting. All right. A circuit 2. Omega circuit 2 over S plus omega circuit 2. And we pick and dot, dot, dot as needed. We pick omega circuit and A circuit such that we meet both specs. So this would have to be larger than our design cutoff frequency. Everyone agree? These are things to think about. Questions?
Like, what are we really doing? Add stages to the circuit, are we adding more to the?
You're putting
overall?
corner frequencies above the cutoff frequency, above the spec sheet, or sorry, the design specification, not the spec sheet, the design specification. So our goal is to just have a overall gain of 10 to the 4th over some frequency range that's much higher than we could do with a single op amp circuit. So you would have to pick each one of these to be higher than 10 to the 5th.
I don't really understand what that means, frequency range of 10 to the 5th. So is that like the?
So I want a gain of 10 to the 4 at 100 radians per second, at 1,000 radians per second, at 100,000 radians per second.
Oh, I see.
But if I just do a single op amp, once I'm at 100,000 radians per second, I'm in the stop band, maybe. Maybe not necessarily for this circuit, but
So,
so I want to make sure that every stage I'm in the pass band instead of in the stop band.
Multiply together would be a collective gain.
Right. So gain multiplies. There is an artifact of if I have a triple pole, then my actual pole is somewhere off to the left at a lower frequency. So that is a small element. So that is a factor. All right. I want to move on to break our op amp in a different way, I suppose. Something that you saw yesterday. So we have the slew rate. And I suppose the slew rate, I always find this kind of a straightforward thing. I'm not sure students do. Slew rate is the maximum rate of change of the output. It's a slope. And it's a slope defined by delta V over delta T. It's a spec sheet value. So again, a spec sheet value, we can go look at our 741. And right here, this is nice and well named. Let's go with red. Give this some contrast. There is our slew rate. Maximum rate of change. What you did in the lab, and hopefully everybody succeeded in this in some sense or another, you input a square wave. If I input a square wave to an inverting amplifier, ideally, what do I expect to come out of the output? No. Ideally, a square wave. I put a square wave in, I expect a square wave out. The signs change, so there's a 180-degree phase shift. In reality, what did we see if we zoomed in? We saw the output did not change instantaneously. That's what a square wave is. It's going from min to max instantaneously. It's going from max to min instantaneously. So I can draw a square wave. This is always a good input signal. Etc., etc. There's my square wave, Vn of t. I'm going to copy that because we're going to ask some fundamental questions here. God dang it. Why does that keep happening? That's not what I copied. Not pasting correctly. There we go. What's that? I'm going to say my square wave is 5 volts, 0 to 5 volts. So here's a T, 0 to 5 volts. There's my input. And we'll do the output with my inverting op amp, the out of T. Here's our circuit. Minus plus 1K, 1K, Vn of T, the out of T. What do we expect the output to look like? What's the gain of that circuit? What's the gain? -1. Here is minus 5 volts. This is the expected output. Right? Everyone agree with that? Let's actually copy that. Slew rate. One volt per microsecond. Let's say my input frequency is 10 to the fifth hertz, or T equals 10 microseconds. And we're gonna, okay with my math? 100 kilohertz, 1/100 kilohertz, 1/100,000, 10 microseconds. And if this is a 50% duty cycle, there is 5 microseconds, 10 microseconds, 15 microseconds. My output wants to do this. Before T equals 0, my output is at 0. And we can say that's an initial condition. It wants to go straight down to -5 right away. How long does it take to go to -5? Slope, I suppose this is plus or minus. This isn't a magnitude concept. 1 volt per microsecond, plus or minus. How long does it take to change 5 volts? 5 microseconds. What's my actual slope? What's my actual output? And here, instantaneously, we want to go from -5 to 0, but it takes 5 microseconds. This is what we would see. Everyone okay?
Because it's has like capacitor characteristics, wouldn't it be more like a
Oh,
swoop?
no, actually, it's fairly linear. Is that you should have seen it being fairly linear in the lab.
Yeah,
Did everybody see it being fairly linear?
it was.
Yeah. At the junctions where it changed slope, you probably saw some RC effects there. There was probably some ripple, something like that. So, all right, let's make our input frequency a little smaller. So we had 10 to the fifth. Let's make it 5 times 10 to the fourth, which means our period is 20 microseconds. And so in this case, we have 10 microseconds, 20 microseconds. And once again, we can look and ask the question, what's going on here? Initially, we're trying to go from 0 to -5 instantaneously. How long does it take? It takes 5 microseconds. Still, that hasn't changed. What happens? Well, God dang it, in half the period or half the cycle, it does this. We get a nice trapezoid. It's the same exact slope as the previous problem, just relatively our period is longer, etc., etc. Everyone agree? All right. Input frequency 1 kilohertz. T equals 1 millisecond. What does my output look like now? I consider this kind of an important question. What does my output look like now? This is a human question. What does my output look like now? I can go label. That's an M in case you can't read.
Oh,
So. No, it's an amp, 1 millisecond. 0.5 M, 1 M, 1.5 M, 2 M. What does my output look like? How long does it take to go from the min value to the max value, or go from 0 to -5? How long does it take? What's that? To go from 0 to -5. How long does it take?
Bye bye.
Still takes 5 microseconds. What does my output look like? It looks like a square wave. Why? There's a slope in there, but we can't see it. So our real output looks something, maybe there's a tiny bit of slope, but we can't really see it. Ugh. It looks kind of like that, etc., etc. The output looks like a square wave. Because of the scale. The 5 microsecond rise and fall times are too small to see. So whenever we've done anything with square waves, there's always been a slope. We just probably couldn't see it. Even for going back to digital systems. When you were putting square waves into flip-flops, there's some slope associated with the output, but we weren't at a scale to see it. Yeah.
What is the input frequency of the
It's just an indication of how long it takes. So it adjusts this time. It's 5 microseconds no matter what. I suppose we could do one more and ask the question, and there's a little bit more complexity to this question than I'm necessarily going to bring up unless you ask me. But let's say, in this case, our input frequency was 2 times 10 to the 5th. So now our period is 5 microseconds. That's a mu, 5 microseconds. So we now have 2.5 mu, 5 mu, 7.5 mu. It takes 5 microseconds to go from 0 to -5 volts. What does my output look like? As I'm going from here, point to stress, the output is always trying to go where the ideal output is. So it's driving. It starts here, as we've already seen, it starts driving towards -5. That's where it wants to be. But what's its slope? At 2.5 microseconds, how far has it made it?
halfway.
Halfway. Excellent. What's that? So what happens now? It wants to go to 0. It no longer wants to go to -5. It always wants to go to the expected output. Halfway. There's a little bit more going on here, but that principle is valid. That the total change over each half period, since the square root over each half period, 2.5 microsecond or 2.5 volts. That's all it has time to change before it's trying to change back to wherever okay. These are real things. So other limiting characteristics of the op amp. Everybody good? Questions? Everybody see the slew rate yesterday? Please don't shake your head. You saw that. Okay. There's another thing, and this is in some of the spec sheets, not in the 741s. Plus, minus. Not plus, minus, minus, plus. We're gonna stick with our inverting op amp. 1K. 10K. The out. The in. The n of t equals 1 sine omega t. We're going to ignore gain bend with product effects, ideally. V out of t equals what? What is it?
Like negative R2 over
Which is what? Negative 10 sine omega t. What haven't I told you? Whenever we build this chip on paper, what do we have to do? When you build, not on paper, on the breadboard, we need power. B power equals plus minus 5 volts. What's the maximum output now? Plus or minus 5 volts. This saturates the output. What does our actual output look like? Well, we can draw our expected output. Here's our expected output, and I'm not going to quite draw it to scale. So there's +1, there's -1. Here's +10. There's -10. Yeah, the scale's not right, but whatever. There's our expected output, right? What's our actual output? Stops at 5. +5, -5. It saturates at +/-5. And technically it would be less than that, as you all saw. But we can assume that we're rail to rail, that we're close to those DC voltage characteristics. So that's called voltage saturation. We've mentioned this before. We don't have time, but we can set it up and leave you with a sleepless couple days in anticipation of this. If we have voltage saturation, what else do we have? If we have voltage, what else do we have? Current. We have current saturation as well. Which has to do with the maximum current sourced or synced from the op amp output. This is not in the 741 spec sheet, but I have seen it in others, sometimes called the short circuit current. So I don't think it's in the 741. Oh, I lied. Sorry. And this time it was an accidental lie, not a deliberate lie. There's our short circuit current. Around 25 milliamps. I forgot. So real characteristic. What does that mean? Well, we know current comes out of the output. What happens if we don't have that current supplied? Our output voltage will not be what we expect. We'll go over that in some detail on Thursday. And that will be the last way that we break our op-amp. All things that we can do where op-amp output does not equal what we expect it to. But what are the limits of our equipment? That's the question we're asking here. It's a big question. When you go off and be an engineer, these are